August 7, 1943. Office of Major General G.M. Barnes, Ordnance Department, Washington, D.C. The letter sat on the general's desk, marked High Priority. Its words carried the weight of combat reports streaming in from every theater of war. Army Air Force's headquarters was demanding action, and the message was clear. American pilots were running out of time. In the skies over Europe and the Pacific, a deadly mathematics was playing out at 27,000 feet. Enemy aircraft were getting faster. The German Messerschmitt Me-262 Schwalbe, the world's first operational jet fighter, screened through the sky at 540 miles per hour. American gunners had mere seconds to acquire their target, aim, and fire before the enemy vanished from their sights. The window of opportunity was collapsing. The problem wasn't the courage of American crews or the skill of their pilots. It was the gun. The AN M2.50 caliber machine gun, mounted in clusters on fighters and heavy bombers, fired at a cyclic rate of 750 to 850 rounds per minute. On paper, it sounded formidable. In combat, against jet-powered aircraft that could outrun and outmaneuver anything the Allies flew, it was simply too slow. The Army Air Forces had calculated the tactical requirements in blood and burning aircraft. They needed a gun that fired at least 1,000 rounds per minute, minimum. Not 950, not 980, 1,000 rounds or better, because anything less meant pilots would continue to return from missions with empty sky where targets used to be, and too many wouldn't return at all. But achieving that rate of fire with a .50 caliber weapon had proven almost impossible. The sheer power of the cartridge, the massive recoil forces, the heat, the stress on every component, it was tearing experimental guns apart. Since 1939, military arsenals and major firearms manufacturers had been racing to solve the problem. Springfield Armory, the legendary institution that had armed American soldiers since 1794, had been working on it. The Colt Company, with decades of firearms expertise, had thrown rare engineers at the challenge. In January 1940, Colt had developed the M2E1, which achieved 997 rounds per minute, tantalizingly close. But the weapon experienced so many malfunctions and parts failures during testing that it was deemed unusable. The vibrations and stresses were literally shaking the gun to pieces. By 1943, millions of dollars had been spent. Nearly 4 years of development had produced nothing the Army Air Forces could use in combat. High Standard Manufacturing Company in New Haven, Connecticut, had been working on the problem since 1942. Their experimental T-22 series guns, the T-22, T-22E1, T-22E2, T-22E4, T-22E5, and T-22E6 had shown promise. Some achieved the required cyclic rate. But each prototype told the same story: stoppages, malfunctions, broken parts. The standard M2 components simply couldn't survive the punishment. The Ordnance Department had even drawn up a list of what they were willing to accept for failure rates in a high-speed gun. At 1,200 rounds per minute, they deemed 5 malfunctions and 1 breakage per 5,000 rounds acceptable. Even with these seemingly attainable requirements, no one could deliver a weapon that met the specifications. 12 days after the first letter, on August 19, 1943, Brigadier General WWII sent another urgent communication to the Chief of Ordnance. The message was the same, but more insistent. Develop an improved, high-speed 50 caliber aircraft machine gun at the earliest practical date. The pressure was mounting. Pilots were dying. The tactical situation demanded innovation. What neither general knew that August was that the solution wouldn't come from a military arsenal or a traditional firearms manufacturer. It would come from a company whose engineers spent their days designing refrigerators and freezers, not weapons of war. The breakthrough was about to emerge from the most unlikely of places, Dayton, Ohio, at the Frigidaire division of General Motors. August 1943. Frigidaire Division, General Motors, Dayton, Ohio. The Frigidaire plant in Dayton had already been transformed by war. The assembly lines that once produced refrigerators and freezers for American households now hummed with military production. Like many American manufacturers, Frigidaire had converted its civilian expertise to the war effort. The company was already manufacturing the standard M2.50 caliber Browning machine gun, one of 4 General Motors subsidiaries producing the weapon that armed American fighters and bombers. But the Ordnance Department wanted more than manufacturing capacity. They wanted innovation. The contract arrived in August 1943, and it was different from anything Frigidaire had received before. This wasn't simply an order to produce existing weapons. This was a development contract, a challenge to solve the problem that had defeated Springfield Armory, Colt, and High Standard. The Army needed a high-speed .50 caliber machine gun, and they were willing to try an unconventional approach. What made this contract remarkable was what it didn't say. The Ordnance Department, frustrated by years of failed attempts to modify the existing M2 design, made a critical decision. They placed no restrictions on the number of changes Frigidaire could make to the weapon. The engineers were free to redesign, reimagine, and rebuild whatever was necessary. The Army had finally recognized that incremental improvements wouldn't work. The .50 cartridge was simply too powerful for the M2's basic construction to handle at speeds above 1,000 rounds per minute. A high-speed gun would have to be fundamentally different. For the Frigidaire engineers, this was unfamiliar territory. They were mechanical engineers, certainly, men who understood precision manufacturing, metallurgy, heat dissipation, and stress analysis. But their reference points were compressors and cooling systems, not firearms. They came from a civilian manufacturing background, not military design. They hadn't spent careers studying ballistics and recoil systems. Yet perhaps that was exactly what the project needed. The team at Frigidaire began where traditional firearms engineers had failed. They didn't start by asking how to make the M2 fire faster. They started by studying why it failed when pushed beyond its design limits. Initial experiments focused on modifying the standard M2 with an air buffer and a redesigned backplate buffer, slightly longer than the standard model. Neither device achieved the desired result. The fundamental problem remained. The architecture of the M2 couldn't handle the increased forces. So they went deeper. If the existing design couldn't be fixed, it would have to be rebuilt from the ground up. The engineers began analyzing every component, every stress point, every source of friction and heat. They approached the weapon the way they might approach a failing refrigeration system, methodically identifying failure points and redesigning around them. By March 1944, Frigidaire had produced their first prototype, the T-25. The weapon incorporated several innovative features. The backplate buffer was completely redesigned, with springs incorporated into the design. The breech-lock depressors, previously located on the oil buffer housing, were relocated to the receiver walls. A muzzle booster was added to help increase the cyclic rate. The gun looked promising. But when the Ordnance Department tested the T-25, it revealed the same pattern that had plagued the high-standard prototypes. The gun was relatively successful, but further development work was clearly needed. The team immediately began work on an improved version, the T-25E1. On May 10, 1944, the T-25E1 underwent testing at Aberdeen Proving Ground, the Army's primary weapons testing facility. The engineers watched as their weapon was put to its paces. It didn't take long for the problems to emerge. Numerous stoppages, parts failures. The testing was stopped before completion. For a less determined team, this might have been demoralizing. They were competing against the combined expertise of America's premier military arsenals and established firearms manufacturers, and failing by the same metrics. But the Frigidaire engineers did something that would prove critical to their eventual success. They learned from everyone else's failures. The next prototype, designated T-25E2, took the best features from all the previous attempts, not just their own work, but innovations from the high-standard T-22E6 weapon as well. The engineers weren't bound by institutional pride or manufacturing traditions. They were problem solvers, and they'd take good ideas wherever they could find them. The T-25E2 was tested in June 1944. Initial results seemed better, but functioning problems appeared immediately. After only 1,800 rounds, the test was stopped. The gun still wasn't ready. But something had changed in the approach. With each iteration, the Frigidaire team was getting closer to understanding the fundamental challenge. They weren't just trying to make an existing gun fire faster. They were creating something new, a weapon that would look like a Browning M2 from the outside, but would be almost entirely different beneath the surface. By summer 1944, as Allied forces pushed inland from the Normandy beaches and American bombers continued their relentless campaign over Germany, the pressure for a solution had never been greater. The Messerschmitt jets were appearing in increasing numbers. Pilots needed that faster gun. In Dayton, the Frigidaire engineers were preparing their next attempt. They designated it the T-25E3. This time, they believed, would be different. July 19, 1944. Aberdeen Proving Ground, Maryland. The T-25E3 arrived for testing with little fanfare. It was another experimental high-speed machine gun, joining a long list of prototypes that had promised much and delivered disappointment. The weapons testers at Aberdeen had seen this story before. Guns that looked good on paper, that incorporated clever engineering solutions, that fired beautifully for the first few hundred rounds, and then began to shake themselves apart. But the Frigidaire engineers knew something was different this time. The T-25E3 represented a fundamental reimagining of the Browning design. They had taken the best features from the high-standard T-22E6 prototype and combined them with their own innovations. The result was essentially a new weapon. From the exterior, it looked like a standard Browning M2. The overall dimensions were the same, the mounting points identical, critical factors for retrofitting existing aircraft. But internally, almost nothing was interchangeable with the M2. The engineering changes were comprehensive and precisely targeted at the stress points that had destroyed previous high-speed prototypes. The bolt had been completely redesigned using advanced metallurgy. Lighter, stronger, faster. That eliminated the forcing of the ejector between cartridges in the ammunition belt, a seemingly small change that dramatically improved reliability in cramped aircraft installations where belts could twist and bind. The accelerator mechanism had been reimagined to make more effective use of the barrel's energy, increasing the bolt's speed during the firing cycle. Where previous designs had used fiber discs in the bolt buffer, the T-25E3 employed a Belleville spring design, cupped steel washers that returned more energy to the bolt, increasing the force of its counter-recoil and contributing directly to the higher cyclical rate. One of the most persistent problems in high-speed gun development had been backplate failures. Under the tremendous forces generated by rapid fire, the backplate at the rear of the receiver would crack and fail. The Frigidaire solution was elegant. They redesigned the backplate to clamp around the receiver, preventing the spreading of the receiver's side plates that had been causing the failures. The breech-lock depressors were rigidly mounted to the receiver's side plates by riveting, preventing the buffer body from moving and improving the stability of other components. Even the breech lock itself had been refined, with a redesigned cam surface for smoother operation. The extractor cam was made substantially larger than that used on the M2. The top cover was redesigned to increase feed lift, incorporating a feed pawl shaped to fit the cartridge and link, along with a strengthened belt feed lever. A split belt holding pawl was added to improve ammunition feeding in confined installations. And there was the muzzle booster, a device that would help push the cyclical rate past the critical 1,000 rounds per minute threshold. The Aberdeen test officers loaded standard ammunition and standard links into the T-25E3. No special components, no hand-selected cartridges. If this gun was going to work, it had to work with the same ammunition every other weapon used. The gun began to fire. The sound was different from the standard M2, faster, a higher-pitched roar as the cyclical rate climbed. The operators watched the counters. 1,150 rounds per minute, 1,200.
The gun stabilized at an average of 1,250 rounds per minute, nearly double the rate of the AN-M2, exactly what the Army Air Forces had demanded in 1943. But cyclical rate alone wasn't enough. High Standard had achieved similar rates with their prototypes. The question was whether the gun could sustain that rate without destroying itself. The test continued. 1,000 rounds, 2,000, 3,000. Malfunctions did occur. But here was the critical difference. It was possible to determine the specific cause of each individual malfunction. These weren't catastrophic failures, weren't parts shattering under stress. These were issues that could be identified, analyzed, and corrected through targeted improvements to specific components. The gun's basic architecture was sound. The fundamental problem that had plagued every previous high-speed prototype, the M2's inability to withstand the forces involved, had been solved. The functioning of the T-25E3 was greatly improved over all previous high-speed prototypes. The Frigidaire engineers had done what the military arsenals and traditional firearms manufacturers could not. They had created a weapon that married the cyclical rate requirements of modern air combat with sufficient reliability for military service. Word of the successful testing spread quickly through military channels. The Army Air Corps and U.S. Navy both immediately requested standardization of the weapon. This wasn't just promising, this was the solution they'd been desperately seeking since 1939. But the war wasn't waiting for perfect engineering. The T-25E3 would need further refinement, additional testing under service conditions. Throughout late 1944 and into 1945, the weapons underwent extensive trials. Each test provided data, revealed areas for improvement, and validated the core design. Meanwhile, production of another weapon was consuming resources. High Standard's work hadn't been entirely wasted. The Ordnance Department had taken the best features from the T-22 series and created the T-36, an improved version of the standard M2 that increased the cyclical rate by approximately 100 rounds per minute and reduced malfunctions. In September 1944, 4 T-36 guns were installed in a P-38 aircraft and tested at Aberdeen. 20,000 rounds were fired with only one malfunction. Both the Army Air Corps and Navy deemed it satisfactory for service. The Ordnance Committee authorized procurement of 31,336 T-36 guns, designated as the M2A1 aircraft. 8,000 had been delivered when something unexpected happened. The procurement was canceled. The reason was simple. Frigidaire had achieved the impossible. Their T-25E3 was so superior to every other weapon, including the improved M2A1, that continuing with inferior guns made no tactical sense. The T-25E3 hadn't just met the requirements, it had exceeded them so dramatically that it rendered other development efforts obsolete. By early 1945, with the war in Europe approaching its final months and the Pacific Campaign grinding toward Japan's home islands, the Frigidaire weapon had proven itself in exhaustive service testing. It was far superior to the standard M2 Browning for aircraft applications. The civilian engineers from Dayton had accomplished what 5 years and millions of dollars of military research had failed to achieve. In April 1945, the U.S. Ordnance Committee took official action. The T-25E3 was standardized as the Gun, Machine, Caliber 50 M3 aircraft Basic. The M2 aircraft was reclassified as Limited Standard for aircraft use. America's fastest machine gun had been born in a refrigerator plant. April 1945. The war in Europe had weeks left. American and Soviet forces were closing on Berlin from opposite directions. In the Pacific, the island-hopping campaign had brought U.S. forces within striking distance of Japan itself. And in aircraft production facilities across America, the new M3 machine gun was finally entering service. The M3 represented a quantum leap in aircraft armament capability. With a cyclical rate of 1,150 to 1,250 rounds per minute, nearly double that of the AN-M2, the weapon transformed the firepower of any aircraft that carried it. The tactical mathematics were striking. A fighter fitted with 6 M3 machine guns had the same firepower as 9 of the older M2 aircraft weapons. In the seconds-long engagements of high-speed air combat, that difference could mean survival. The weapon measured 57.25 inches in overall length and weighed 63.5 pounds, with a belt lift capacity of 35 pounds. Despite being loosely based on the M2 design and maintaining essentially the same exterior dimensions and appearance, the M3 was fundamentally different. Most parts were not interchangeable between the two weapons. The Frigidaire engineers had rebuilt the Browning from the inside out. The increased diameter of the backplate buffer was visible to anyone familiar with the M2. The recoil booster added length to the weapon. But the real innovations were internal. The lighter bolt, designed using advanced metallurgy, the extractor with its reversible ejector, the redesigned accelerator that made more effective use of the barrel's energy, the Belleville spring bolt buffer with its cupped steel washers replacing fiber discs, the breech lock depressors rigidly mounted to the receiver side plates, the redesigned breech lock cam surface, the enlarged extractor cam, the backplate that clamped around the receiver to prevent spreading, the strengthened top cover with its improved feed mechanism. Each change addressed a specific failure point. Together, they created a weapon that could sustain rates of fire that would have destroyed earlier designs. But the M3 arrived at a bittersweet moment in history. Only 2,400 of the guns were procured before World War II ended in September 1945. The weapon that pilots had desperately needed in 1943 that could have changed the calculus of countless air battles over Germany and Japan came too late to make a significant impact on the war that had driven its development. Germany surrendered on May 8, 1945, just weeks after the M3's official adoption. Japan surrendered on August 15, following the atomic bombings of Hiroshima and Nagasaki. The war was over. The massive military production machine that had consumed American industry ground to a halt. Contracts were canceled, plants converted back to civilian production. At Frigidaire, the engineers who had solved the impossible problem returned to designing refrigerators and freezers. The M3 might have become a historical footnote, an engineering triumph that arrived too late, except that the peace didn't last. On June 25, 1950, North Korean forces crossed the 38th parallel, invading South Korea. The United States, under UN authority, committed forces to defend South Korea. American aircraft, many of them propeller-driven fighters left over from World War II, again needed the most effective weapons available. The M3 machine gun was pulled from storage and put back into production. Several new contractors began manufacturing the weapon. The guns were installed on F-51 Mustangs, F-4U Corsairs, and other aircraft flying combat missions over Korea. The M3 finally got its war. Pilots found that the increased rate of fire gave them a decisive advantage in the brief, violent engagements that characterized air combat over the Korean peninsula. The weapon performed as designed, delivering the firepower that the Army Air Forces had demanded back in
1943. But the extended combat use in Korea revealed a troubling pattern. Despite all the improvements in design and metallurgy that Frigidaire had implemented, despite the careful engineering that had solved so many of the problems that plagued earlier high-speed prototypes, the M3 had a malfunction and failure rate that proved unacceptable for sustained service. The weapon was pushed beyond its limits in Korea, firing burst after burst in combat conditions far more demanding than any testing program could simulate. Sears broke, bolts cracked, other parts failed under the relentless stress of sustained high-speed fire. The same fundamental problem that had destroyed the Colt M2E1 in 1940 and the high-standard T-22 series prototypes in 1942 and 1943 was still present, just pushed further back. The M3 had extended the boundaries of what was possible with a .50 caliber machine gun, but it hadn't eliminated the basic physics of the problem. The cartridge was simply too powerful, the forces too extreme for any mechanical system to handle indefinitely at those cyclic rates. By the end of the Korean War in 1953, the future of the Browning .50 caliber machine gun as an aircraft weapon appeared very bleak.
The rapid-firing M3 model had proven too problematic for sustained use. The older M2 aircraft basic version fired too slowly to successfully engage the increasingly faster jet aircraft that now dominated military aviation. The age of the 50-caliber aircraft guns seemed to be ending. Fighter jets were being fitted with 20mm cannons. New technologies were emerging: missiles, sophisticated fire control systems, electronic targeting. The Browning design, created by John Moses Browning in 1918 when Model T Fords and biplanes were considered modern, seemed destined for obsolescence. The M3 was dropped from the U.S. military inventory in the late 1950s. The weapon that required 5 years and millions of dollars to develop, that represented the pinnacle of what could be achieved with the Browning action, had served for less than a decade before being declared surplus to requirements.
The Frigidaire engineers' triumph seemed to have ended not with recognition, but with quiet retirement to military storage depots. But the story of the M3 wasn't finished. The weapon that had been developed too late for World War II, that had served briefly in Korea before being abandoned, would rise again, decades later, rebuilt with new materials and technologies that the 1944 engineers couldn't have imagined. The M3 sat in military storage through the late 1950s and 1960s, a relic of an earlier era. During the Vietnam War, the aging aircraft Browning 50-caliber gun was largely overshadowed by modern weaponry: 7.62mm miniguns that could fire thousands of rounds per minute, 20mm Vulcan cannons with even more devastating firepower. Helicopters, which dominated the Vietnam battlefield, were generally fitted with 7.62mm miniguns or M60 machine guns. The .50 caliber Browning had been relegated primarily to a ground role, mounted on vehicles and tripods for infantry use. The Medusa, the affectionate nickname for the M2 Browning, continued to serve faithfully in these applications. John Moses Browning's 1918 design had proven remarkably enduring as an infantry and vehicle-mounted weapon, but its heyday as a primary aircraft armament seemed permanently finished, replaced by sophisticated missiles and super-fast-firing cannons. Then, decades after the M3's development, something unexpected happened. Military planners began to recognize limitations in the new generation of aircraft weapons. Missiles were powerful but expensive, and had minimum engagement ranges. The multi-barrel cannons were effective but consumed ammunition at such prodigious rates that aircraft could empty their magazines in seconds. And in the conflicts that emerged in the Middle East and Afghanistan, a different kind of warfare was taking shape, one where helicopters and low-flying aircraft needed weapons that could engage ground targets with precision and sustainability. The old reliable .50 caliber Browning was resurrected for modern aircraft applications, primarily on rotary wing aircraft. The M213, a Vietnam-era modernization and adaptation of the AN-M2 aircraft machine gun, was briefly fielded from 1968 through 1974 as a pintle-mount door gun on UH-1D and UH-1M Iroquois helicopters, the famous Hueys. Other variants followed. The M296 was developed for remote firing applications on the OH-58 Kiowa Warrior helicopter. The GAU-15/A became a modern aircraft-mounted derivative for H-46, UH-N1, and H-53 series aircraft. The GAU-16/A featured improved trigger mechanisms. The GAU-18/A, formerly designated M218, was a lightweight variant used on Air Force MH-53J Pavelo II and HH-60 Pavehawk helicopters. All of these were based on the standard M2 design, with cyclic rates in the 750 to 850 rounds per minute range. Reliable, proven, effective for their intended roles. But they weren't the super-fast gun that the Frigidaire engineers had created. Then, in the late 20th century, someone looked at the old M3 design with fresh eyes and new technologies. The fundamental concept that the Frigidaire team had proven in 1944 was sound. A high-speed 50-caliber machine gun could deliver dramatically superior firepower. The problem was materials and metallurgy. The M3 had pushed 1940s manufacturing technology to its limits and slightly beyond. But by the 1990s and early 2000s, material science had advanced considerably. High-grade alloy metals, improved heat-treating methods, and manufacturing tolerances that would have been impossible in 1944 were now standard. Engineers redesigned the M3 series using these modern capabilities. The most obvious mechanical change was reconfiguring the weapon's operating system to fire from the open bolt position. This permitted the weapon to be fired in longer bursts without the danger of overheating and causing a cook-off, when residual heat in the chamber ignites a chambered round without the trigger being pulled. The result was the M3P model, a fixed, remote solenoid-fired version. The weapon measured 66.14 inches in overall length with an unmounted weight of 80.25 pounds. The barrel length was 35.2 inches. And the cyclic rate, the number that had driven the entire development program back in 1943, was 950 to 1,100 rounds per minute. Not quite the 1,250 rounds per minute of the original M3, but far faster than the standard M2, and with reliability that the 1945 version could never achieve. The M3P was deployed on the ANWTQ-1 Avenger air defense system and some versions of the UH-60 Blackhawk helicopters. The Avenger system used the M3P to cover the missile dead zone and engage ground targets. The machine gun was mounted on the right launch beam with its ammunition magazine fixed on the right side of the turret, carrying 250 to 400 rounds of 12.7mm ammunition. Routine maintenance procedures included scheduled replacement of selected high-stress parts to ensure system reliability, a recognition that even with modern materials, a high-speed 50-caliber gun required careful maintenance. In 2004, another variant was adopted, the M3M flexible machine gun, designated as the GAU-21/A by the U.S. Air Force and Navy. This version was designed for pintle soft mount applications on helicopters and fixed-wing aircraft, and could also be mounted in vehicles. The weapon measured 59.8 inches overall, weighed 78.9 pounds, and had a barrel length of 36 inches. Its maximum cyclic rate was 1,100 rounds per minute, firing from an open bolt position. The M3M was marketed as a complete weapon system consisting of 3 parts: the weapon itself, a medium pintle head soft mount, and a cradle used to integrate the system into a vehicle or aircraft. The grips and fire control were mounted on the pintle mount rather than the weapon, providing better control and isolating the gunner from the gun's vibration. The soft mount absorbed and reduced both recoil and counter-recoil forces to 1/3 of that experienced with the M2 and M218 weapons. The M3M had significant advantages over earlier systems. Its 1,100 rounds per minute cyclic rate delivered dramatically superior firepower, and its barrel life was estimated at 10,000 rounds. The weapon could fire a 600-round continuous burst without damage to the barrel, a capability that would have been impossible with the 1945 M3.
There were 3 sight options available: open ring sights, optical sights, and laser sights for day or night operation. The Frigidaire engineers' concept had been vindicated. 60 years after they created the T-25E3 in a Dayton factory, their fundamental design was serving on modern military aircraft, finally achieving the reliability that had eluded the original version. The civilian mechanical engineers who had approached the problem with fresh perspectives, who had been willing to completely redesign the weapon rather than incrementally modify an existing design, who had solved the impossible problem that defeated military arsenals and traditional firearms manufacturers, their work had endured. The M3 Browning had traveled a long and unlikely path. Conceived in desperation during World War II, developed by refrigerator engineers, arriving too late to impact that conflict, serving briefly in Korea before being abandoned, and then resurrected decades later with modern materials to finally fulfill its original promise. The story of the M3 Browning machine gun stands as one of the most remarkable and least known engineering achievements of World War II. It is a story without the drama of Manhattan Project physicists splitting atoms, without the public recognition given to the designers of fighter planes and bombers, without the fame that surrounded other wartime innovations. Yet it represents something equally important: the triumph of unconventional thinking over established expertise. When the Army Air Forces sent their urgent letters to the Ordnance Department in August 1943, they were admitting failure. 5 years of development work by America's premier military arsenals had produced nothing serviceable. Springfield Armory, with its 149 years of weapons manufacturing experience, couldn't solve the problem. The Colt Company, legendary name in American firearms, had failed. High-standard manufacturing, with their series of T-22 prototypes incorporating increasingly sophisticated modifications, had gotten tantalizingly close, achieving the required cyclic rate, but couldn't create a weapon that wouldn't shake itself apart. The fundamental challenge seemed insurmountable. The .50 caliber BMG cartridge was simply too powerful for any mechanical system to handle at speeds above 1,000 rounds per minute. Every attempt to push the Browning design beyond its limits ended the same way: broken sears, cracked bolts, shattered parts. The forces involved were too extreme, the stresses too great, the heat too intense. Then the Frigidaire division of General Motors, a company known for refrigerators and freezers, solved it in less than a year. How did civilian engineers succeed where military weapons experts failed? The answer lies not in superior technical knowledge. The Frigidaire team didn't know more about firearms than Springfield Armory's gunsmiths. Rather, they succeeded because they weren't constrained by firearms tradition. They didn't approach the M2 Browning as a sacred design that needed careful, respectful modification. They approached it as a mechanical system with failure points that needed to be eliminated. When the Ordnance Department gave Frigidaire the contract in August 1943, they made one critical decision that changed everything. They placed no restrictions on the number of changes the engineers could make. Previous development efforts had tried to maintain compatibility with existing M2 parts, to minimize manufacturing disruption, to preserve the essential character of the Browning design. The Frigidaire team had no such constraints. If a component needed to be completely redesigned, they redesigned it. If advanced metallurgy could create a lighter, stronger bolt, they used it. If the backplate needed to clamp around the receiver instead of attaching in the traditional way, they made that change. The T25E3 that emerged from their Dayton factory in 1944 looked like a Browning M2 from the outside. It had to. It needed to fit existing aircraft mounts, use standard ammunition and links, integrate into established logistics and maintenance systems. But internally, it was almost entirely new. Few components were interchangeable with the M2. Every stress point had been analyzed and reinforced. Every source of friction reduced. Every heat generation point addressed. The M3 achieved an average cyclic rate of 1,250 rounds per minute using standard ammunition and links, exactly what the Army Air Forces had demanded and what 5 years of military research had failed to deliver. The M3's service life tells the story of technology ahead of its time. Only 2,400 were produced before World War II ended, too few and too late to significantly impact the conflict that drove its creation. It served in Korea, finally seeing the combat for which it was designed, but the sustained stress of warfare revealed that 1940s metallurgy still couldn't quite handle the punishment. The weapon was retired in the late 1950s. But the fundamental design was sound. When modern materials science caught up to the Frigidaire engineer's concept, when high-grade alloy metals and improved heat-treating methods became available, when manufacturing tolerances improved, the M3 was resurrected. The M3P and M3M variants, adopted in the early 21st century, finally delivered both the high cyclic rate and the reliability that had been mutually exclusive in 1945. Today, variants of the M3 serve on American military helicopters and vehicles. The weapon system that began as an emergency wartime development program that was created by engineers who normally designed household appliances that arrived too late for the war that needed it, continues to serve 80 decades after its inception. The .50 M2 Browning machine gun, Ma-Deuce, has the honor of being the longest-serving weapon in the U.S. arsenal. It has been in continuous service since the 1920s, a tribute to John Moses Browning's genius. But the M3 represents something different, proof that even a brilliant design can be reimagined, that civilian expertise can solve military problems, and that sometimes the solution to an impossible challenge comes from the most unlikely source. When the Ordnance Committee standardized the T-25E3 as the M3 in April 1945, they recognized an engineering achievement that had required thinking beyond the boundaries of traditional firearms design. The Frigidaire engineers had succeeded not despite their civilian background, but perhaps because of it. They weren't trying to perfect the Browning design. They were trying to solve a problem, and in the end, that made all the difference. The men who designed refrigerators created America's fastest machine gun. It remains one of the most remarkable and least known success stories